Okay, so now we want to review the chain rule, but we want to speed up. We want to do it faster. So we're going to be working with the chain rule and being able to kind of do the speed chain. Okay, so let's start with an example. So let's take the derivative with respect to x of sine of x squared plus 1. So just follow along, and you copy this down as we go. So you may, hopefully you recall, the long way of doing this is to rewrite this as f of g of x, okay, or just f of g and g of x. So we have two links in a chain. We have a function inside of a function. The key is this is a composite. We're not multiplying, we have a function placed inside of a function. The inner function is x squared plus 1. Sometimes it's easiest to identify that. Okay, so that's what we will call g. And then we have the sine of that inner function, so we'll call that the sine of g. And then the long way was to write df dg and dg dx. And df dg would be the cosine of g, and dg dx would be 2x. And we can rewrite the cosine of g as the cosine of x squared plus 1, since that's what g was. And then the key was the idea if I take df dg times dg dx, we should end up with df dx. Right? So just underneath df dg times dg dx, we link together the g's, and that gives us the rate at which f is changing with respect to x. So it's kind of like we translate our currency from dollars to, I don't know, to pesos, and then pesos to riads or something. So we just have two steps of exchange to find the rate at which f is changing with respect to x. Then the answer would be the product of these two things. So we could say that the answer is 2x we should write first. You always write the simpler functions first. We usually put our trigonometric functions at the end. So constants always go in the front and negative signs would go in the front. So this is the answer to that. Okay. Now there's a faster way to do this. Okay, so when I see this writing out that whole table, that's great. And I say always write the table if you aren't going to get it right otherwise. But we want to get much faster at this. You will need to for next year because if you have to write all of this out every single time, it just gets painfully slow. So what you need to do is you have to realize, so the fast way is to recognize mentally that you have a function inside of a function, right? And the key was in the previous thing is we're going to take one of the derivatives times the other. In this case, we have the outer derivative and the inner derivative, and we multiply them. So it really doesn't matter if you go inside out or outside in, right? So if I were to go outside in, what I would do is I would first recognize that I have the cosine of something, okay? And it's the entire inner function, so that would be x squared plus 1. So that was the outside ring. And then I need to multiply by my inside ring, which is, so the derivative of what's inside is 2x. Now that's not the best way to write it. We always want to move the 2x to the front, so I would have to rewrite this as 2x cosine of x squared plus 1. If I'm doing outside in, I often just leave a little space in front so that I can do the inside step second, but place it in front of the outside step to save the translation step. I also could have gone inside. If I want to go inside out, let me just do that again. So what I want you to do to show me your work is simply circle the rings. So inner ring, outer ring. We have an outer function with an inner function in it. So when I go to take the derivative, inner function looks like, basically do the simpler derivative first if you want it to come out in the right order without having to rearrange it. So the inner derivative is 2x. The outer derivative will be a cosine. But remember, it's not cosine of x, it's cosine of the inner function. So if you can show me your work by simply circling the rings and then writing the answer. All right. So continuing along, let's do a series of problems here. Okay, so the first series, that's right, series 1. You want to get good at this just by practicing quickly. Okay, we want to take the derivative with respect to x of the sine of 2x. Okay, so circle the rings. Inner ring is 2x, outer ring is the sine function, right? So then quickly, the answers, I think this is easiest to go inside out. So the inner ring has a derivative of 2. The outer ring is the cosine function, but that's a cosine of 2x, and you have the answer, right? Let's do the derivative with respect to x of the sine of x over 2. All right, so circle your rings and see if you can get the answer, and I'll give you come back in a couple of seconds. There are the rings. You need to remember that x over 2 is the same as 1/2 of x. Hopefully you remember that. And therefore, the derivative of the inner ring is 1/2. Outer ring is the cosine of x over 2. Let's do a couple more in this series. Let's do, you often see pi's as part of the argument of sine of trig functions in general. So let's do this one. Go ahead, circle it, get the answer. Inner function has a derivative of pi. Outer function, it's a cosine of pi x. Back again, it's optional whether to put the parentheses in. Mathematicians often don't when it's a product. So one more in this series. Make sure you're writing all of this down in your notebook and practicing as you go. Let's just throw in something a little more complicated. Let's do usually mathematicians would throw in the parentheses at that point. Go ahead, the parentheses actually make your job easier. Go ahead and get the answer. The inner function is what's in parentheses, so its derivative is just 3 pi over 2. And then we need to have a cosine of the whole inner argument. Okay, so that's series 1. Let's move on to series 2. Let's work with e to the x. All right, so this should be relatively easy. Hopefully you realize the argument, okay, of e is 5x in its exponent, and then there's an outer ring that goes around here. Okay, so we know how to do e to the x. That's the easiest one ever. But we need to do e to the 5x. So I think, once again, this is easier to go inside out. So the derivative of 5x is 5. The derivative of e to anything is e to the same thing back again. So e to the 5x back again. Right? Just do a couple more of these. Well, this one had thrown a few of you on a loop for a loop on a previous test. Remember, that's just -1 times x. Go ahead and solve that. Okay, so remember, show your work. That's your work. And so -1, you don't have to write the 1, is the answer. Okay, so another one of these. Go ahead, beat me to it. That's the answer. Next one. Beat me to it. The circles are your work. That's the answer. And the last one in this series. So let me just add one more because I know we sometimes have trouble with this. Let's do 3e to the 2x. Okay, and let me just comment on this one. I don't think any of you have trouble at this point with the 2x part. It's the 3 times e to the 2x that gives some people trouble. The derivative of 3e to the x would just be 3e to the x. Remember, you can factor a constant out and then take the derivative of what's left. And then that would give you 3. So let me start over. So the derivative of 2x is 2 times 3e to the 2x. So the answer is just 6e to the 2x. And if you can take it directly to the answer, that's good. Just don't let a constant, a little thing like a constant in front throw you off. If there's a constant in front, just you can factor it out and then multiply back by the constant when you take the derivative. So don't let that throw you off. You should be well past being confused by that by now. Okay, so let me just throw in another series. So this one, very common when you're working with sines and cosines that you have a linear function inside. Let's do this one together. So let's just recall, what does this do? This moves the function, this moves the cosine right by 1. Should say translates it, okay? And this is a multiplier. This is a little bit bigger than 1, so it compresses horizontally. Or in terms of this, it oscillates faster. So you can change the frequency at which the cosine is oscillating with that number right out there. So this is very common if you're dealing with anything that oscillates. It'd be very common to have something like this. But we can follow our pattern. We have an inner function, which is everything in the parentheses. So it actually makes it very easy. You need the parentheses this time, by the way, because you have multiple factors. Although actually it's 2 factors, so you wouldn't need the parentheses, but they'll often be there. When it's multiple terms, the parentheses are needed. So once again, this is a 2-step problem. I think it's easiest when you're working with the trig functions to do inside out. So what would the derivative of the inside be? Put the pi over 2 on hold. Okay, that's a constant, so I'll put that on hold. And the derivative of x minus 1 is just 1. Multiply back by the pi over 2. So the derivative of the inside is pi over 2. By the way, that's the slope of the line. If you think of what's in the parentheses, okay, the slope and graph it, it would be a line with a slope of pi over 2. And now we're working with a cosine. So the derivative of that will be negative. Let me put the negative in front of the pi over 2. It's always good to leave a little room as you're doing things. So it'll be a negative sign of the inner function back again. Okay, so that's how we do that. So yeah, it's always good when you know there's going to be a negative in the derivative, leave a little bit of space. Let's work on a few more in this series, or just one more actually. So I want you to be able to do this. This time we don't have factors inside of the argument. We have multiple terms. Don't be confused by the pi's. When you go to take the derivative, the second term right here is just a constant. So don't be confused by that. And pi is just a number. All right, so once again, don't be confused by that. Go ahead and get your answer. Okay, so I should circle these things. And by the way, there's nothing to solve here yet because I didn't actually in front of these write take the derivative. I should have written take the derivative. Otherwise, what I have on the other side of the equation is wrong. So the derivative of that would be, look at the inside, the derivative is simply pi. It's a linear function with a slope of pi. There's going to be a negative because the derivative of cosine is negative sine, and then it's just the negative sign of everything that was inside of the parentheses back again. Okay, so that's how you do that one. Let's move on to one that's trickier. So far everything has had one function inside of another. Let's look at a more complicated series where when we go to take the derivative, this is what we used to call the Chute chain. So we'll keep our functions simpler, but there are 3 layers here. Okay, so we have an f of g of h of x. But if you recall from before, and if I want to find what df dx is, I should be able to simply take df dg times dg dh times dh dx. We simply have a chain with another set of links. We link f to h first, and then h to x. So the product of the 3 things will get us the answer. So if I'm just trying to do this, I could write out all of the terms, but let me do it by circling. So my innermost function is x squared plus 1. Outside of that, we take all of that to the 1/2 power. And we talked about that on the memory list. And then we take the cosine of all of that. So we have 3 layers here. So if I want to get the answer, I start with the inner layer. And we'll probably, when it's 3 layers, you probably want to write it and then clean it up. So if I go inside out, the inner layer has a derivative of 2x. Then we have the square root of something, all right? But if you recall from our memory list, that's it's x to the half. And so we end up with 1/2 x to the negative half, which was the square root of something. Now this time it's the square root of x squared plus 1. So its derivative is 1/2 of the square times the square root of, and then you have to put the x squared plus 1 back in. Okay, so that's the middle circle. Okay, and then we have a cosine, so that will go to a negative, let me put this in parentheses, the negative sign of everything that's in the middle circle. So everything that's in the middle circle is the square root of x squared plus 1. All right, so we have the 3 layers, the derivative of the first layer right here, the derivative of the second layer, and remember then we just write the first layer back into that derivative. And then we take the derivative of the third layer with both the first and second layer nested back inside. This could get cleaned up algebraically. First of all, hopefully you notice there's a 2 and a 2. There's a negative sign here, so let's attend to those first. So the 2's cancel, we're going to have a negative answer. It looks like it will be a fraction of some sort. This first x goes in the numerator. The square root of x squared plus 1 goes in the denominator, and then you have a choice. You could write the sign in the numerator or just write it as a factor afterwards. I think usually it would be written this way because the what's here is a rational expression, and so we probably would put that in front of a sign expression. So all of this actually sort of becomes the amplitude of the sine function. So it's a changing amplitude as x changes. Okay, so that's series 4. Let me have you do one. This will be, we're going to change where the square root is. Let's do the square root of cosine of x squared plus 1. Okay, so put in your circles. Try to take, there will be 3 layers this time. take the derivative of each layer one at a time. I'll pause for a few seconds here and give you time to try to do it yourself. Okay, so here are the layers if you didn't get that. There's layer 1, layer 2, and layer 3. Go ahead and try to take the derivatives if you haven't already. Layer 1 has a derivative of 2x. Layer 2 is going to be the negative sign of the inner layer of layer 1. And then we have, it's going to be a little bit messier, we have the outer layer, which is a square root. So that's something to the half power. So that will end up being half of something to the negative half. And what goes inside of the square root is everything in layer 1 and layer 2. This will simplify. There's a negative overall. The 2's will cancel again. So you can see those 2's will cancel. This negative will come out in front. And then when you look at this, this time I probably will write it with the sign of x squared plus 1 over the square root of the cosine of x squared plus 1. So that's the best way to write that answer. Hopefully you were able to come up with that on your own. Okay, let's do another series. Let's do the inverse tangent of x squared. This is a 2-layer one. So see if you can remember how to do this. Obviously, we're taking the derivative. X squared is the inner layer. The inverse tangent is the outer layer. The derivative, oh, this is series 5. The derivative of the inner layer is 2x. And hopefully you remember that the derivative of an inverse tan is 1 plus something squared. Here's the tricky part. You may have written 1 plus x squared, but that was when it was the inverse tangent of x. We have to put the entire inner layer in to this. Okay, so the argument of the inverse tan is x squared. So we need to square x squared. So this simplifies. We can write 2x over 1 plus x to the 4th as our answer. Let's do one more with the inverse tan, that we'll have 3 layers. Okay, so go ahead and see what you can do. In a little bit, I'll start on it. Identify your layers first. One, 2, 3. The layers have derivatives to layer, inner layer 2x. Next layer is that square root layer, so it's 1 over 2 times the square root of the inner layer. And then you have the inverse tangent, so it's 1 over 1 plus, be careful, something squared. What gets squared? The whole inner 2 layers. Okay, now this will simplify. We look at this, we're going to have one big fraction. The 2's cancel, so the only thing left in the numerator is x. The denominator first has an x squared plus 1 times, now be careful, it's 1 plus this quantity, so don't just multiply it through. So I have a 1 plus, and then we're squaring a square root, so this becomes x squared plus 1. Oh, and it was plus 1 again, so let's just, in one step, let me erase that 1. This will end up being a 2, or x squared plus 2, if you like, because when we squared the x squared plus 1, or the square root of x squared plus 1, we have an x squared plus 1 again. So this is the answer. Okay, we'll move on to another series.